Okay, this is Chapter 8, Problem 71, with some small extension. So in this problem, we're supposed to imagine a scenario in which our sun eventually collapses into a white dwarf, losing about half of its mass. So you can read that as it loses half of its mass in the process, and winding up with a radius that's 1% of its existing radius. Assuming that the mass that's lost gets carried away, not taking any angular momentum away, first thing we're supposed to get is what would the new rotation rate be for the sun, and corresponding to that, what would be its new rotational period. Okay. Second thing is, or if you like, B is what would be its final kinetic energy in terms of the initial kinetic energy of today. So let's have a picture. You got the sun with a rotation rate of approximately 30 days at the moment. So it's spinning around. Let's suppose this is its axis, and it's got an initial omega, which you can go ahead and write this as 2 pi for the initial period. And then later on, it's lost half of its mass, but it's also very, very small. So it kind of looks like this. So I'll write this as m, and this is an m over 2. Its radius is supposed to be 1% of the original, so this is not drawn to scale, but you get the idea. It's now rotating at some new omega final, which is equal to 2 pi over the final period. We're going to figure out things like what is the final period and what is the kinetic energy. So conceptually, what we've got, we're told that the lost mass carries away no angular momentum. That's a huge hint to use conservation of angular momentum. Conservation of angular momentum, I don't know what abbreviation I would have used in class, but there you go. Conservation of angular momentum. We also are going to be interested in rotational kinetic energy for this object spinning around. So we'll have rotational kinetic energy. And that should be enough to get us going. Equations. We have conservation of angular momentum. In other words, L initial is equal to L final. Okay, L is angular momentum. What is L? It's defined as the moment of inertia of that object times its angular speed. The moment of inertia for a sphere is something that we kind of need, but you'll see the actual detailed form of it isn't super important. But for a sphere, 2/5 m times its radius squared. Rotational kinetic energy, I'll write that as k rot, is 1/2 I omega squared. I've already written this down, but remember that there's a relationship between angular speed and the period. The angular speed, the number of radians per unit time it goes through, well, it goes through 2 pi rotations in every one period. So omega is equal to 2 pi is the relationship we need. Okay, so part A, what would be the sun's the new rotation rate? We're going to use conservation of angular momentum to figure this out. So what we have is initial moment of inertia, initial angular speed equal to final moment of inertia, final angular speed. We have to be really careful as we go through this and make sure that we're not making any assumptions. Initially, we have an object whose moment of inertia 2/5 times its mass, its original mass, times its original radius, whatever that is. They didn't give us those numbers. Hopefully we won't need them. And its initial rotational rate. In the end, it's still a sphere, we assume. Same formula, 2/5. Now its mass, I'll put this in parentheses, is half of what it was. And I should put this as an Ri. It started off with some initial radius Ri. It ends up with a final radius Rf. So that means over here I should put Rf squared and final rotational rate. I think so far we've been pretty careful and we're in decent shape. Let's clean this up a little bit. The 2/5 cancels, which again reminds you that it didn't really matter so much what its moment of inertia was. The initial mass doesn't matter either. All we need is the fact that it's half of what it was before. Go one further step and remind you that, so what's left here is the 1/2. Put this over here, Ri squared. This RF, we're told, is 1% of the original. So what that means is this is 0.01 Ri and square it, which means that even the initial radius doesn't matter. Right? The Ri gets squared. What we have on the right is 0.01, or 10 to the minus 2 squared. That's 10 to the minus 4. And then with a 1/2, that makes this 5 times 10 to the minus 5. Okay? In other words, the initial rotation rate is much, much smaller than the final rotation rate. What we're expecting to find is that this white dwarf that forms is spinning very, very fast compared to the original spinning rate of the sun beforehand. So you can now answer part A and part A prime to figure out what is the new rate. What we'll do is take this 5 times 10 to the 5 to the other side and write this as 10 to the 6. Let's just cheat slightly. If I instead turn this into 2 pi over ti equal to 5 times 10 to the minus 5, 2 pi over tf, my 2 pi's cancel, and I can find the new period in terms of the old period. In other words, the final period is much smaller than the initial period. This is the 30 days. And then I'll let you convert that into seconds. What you should find that this is approximately a little more than 2 minutes or so. I get this to be about 130 seconds. Okay. If you then convert that into angular speed, what you should find is a nice approximately 5 times 10 to the minus 2 radians per second. The reason why I'm having you get this as well is we need it for part B. Okay. Part B is just a matter of what is the new kinetic energy compared to the old kinetic energy. So why don't we go ahead and write this ratio down. The final kinetic energy in terms of the initial kinetic energy, or that ratio. So let's think very carefully. We've got a formula, 1/2 moment of inertia, 2/5 times the mass. Again, it's the original mass over 2 times the radius squared, but it's that radius is given by 0.01 times the initial radius, and we have to square that. Okay, that is the moment of inertia times the final rotation rate squared. Divide this by the initial, which is 1/2, the 2/5, the m, and the Ri squared, and the initial. Okay. Of course, the 1/2s cancel, the 2/5 cancel, the mass cancels, the R cancels. What you end up with, I'll just put the intermediate step. There's a leftover factor of 1/2 times 0.01 squared. That's the 5 times 10 to the minus 5. And then the ratio of omega final squared over omega initial squared. So I'll write that here. If you want, you can do that in terms of the period. That turns out to be the period initial squared over the period final squared, because these things are inversely proportional to the periods. In any case, what you find is that this is approximately 20,000. That's the interesting result here, is that in the end, the kinetic energy is about 20,000 times bigger than what it started with. And part C is for you to think about deeply, where does that extra kinetic energy come from?